Section 2.6, a taste of unsupervised learning. Now that we have explored key aspects of supervised learning in the sections above, let us get a taste for the basics of unsupervised learning. In this context, the data is unlabeled and is denoted via D, which is x1 through xn. Here we assume that each sample or observation xj is a p-dimensional vector of features in Euclidean space. Observe that there are no labels, yj. We briefly introduced two popular unsupervised learning methods, one for clustering and one for data reduction. These are respectively the k-means algorithm and the framework of principal component analysis, PCA. In exploring PCA, we also take a slightly deeper look at the linear algebraic concept of singular value decomposition, SVD, already used in section 2.3 in the context of pseudo-inverse representation. Here we see how SVD has applications to data compression, a notion sometimes used in more complex deep learning models. Further reference to more advanced supervised learning methods are in the notes and references at the end of the chapter. K-means clustering. The machine learning activity of clustering allows us to identify meaningful groups or clusters among the data points and find representative centers of these clusters. The aim is that the samples within each cluster are more closely related to one another than samples from different clusters. Formally, for the dataset D, clustering is the act of associating a cluster L with each observation, where L comes from a small finite set, 1 through k. That is, a clustering algorithm works on the data D and outputs a function C, which maps individual data points to label values, 1 to k. The cluster data algorithm output is then a collection of clusters denoted via CL, so each cluster CL, for L going 1 to k, you have k clusters, is a collection of all data points xj, such that the clustering function of xj equals L. A clustering algorithm attempts to choose a cluster such that the elements of each CL are as homogeneous as possible. The k-means algorithm is one very basic, yet powerful heuristic algorithm. With k-means, as with several other types of clustering algorithms, we pre-specify a number k, determining the number of clusters that we wish to find. Hence, k may be treated as a hyperparameter. As the algorithm seeks the function c, or alternatively the partition of clusters c1 through ck, it also seeks representative centers, also known as centroids of the clusters, denoted by J1 through Jk, each an element of Rp. One may view the ideal aim of k-means minimization as minimization of clustering cost, which is represented as the sum over all clusters, and then for all of the elements of a given cluster, so this cluster is part of the decision variable, find the difference between the elements and the center of the cluster. And the center is also a decision variable. And take this is a vector, and that's the norm squared of the vector. Okay, so the mean square error per cluster. Such minimization is generally computationally intractable, since it requires considering all possible partitions of D into clusters. Yet, it can be approximately minimized via the k-means algorithm using a classic iterative approach. The k-means algorithm does this by separating the problem into two subproblems, or subtasks, called mean computation and labeling. We define these now. So here's mean computation. Given C, which is your clustering function, or the clustering sets C1 through Ck, where the bars around each CL denotes the number of elements in the cluster L, find J1, Jk that minimizes 239, and you do this via JL is just going to be the mean of all of the points in the cluster. So you take the sum of all of the vectors in the cluster, you're summing up vectors, and you're taking their average. So you're doing per coordinate average. And you do this for all clusters. And then you got your centers, J1 through Jk. Here, each JL is a vector obtained via the element weights average over all the vectors in CL, where each of the P coordinates is averaged separately. That's called mean computation. Labeling. Given J1 through Jk, and assuming these values are fixed, find C that minimizes 239 for every xd. This is done by setting C of x, the cluster of some point x, is just going to be the finding the center over all possible centers that's closest to it. Okay, that's what this equation means. That is, the label of each element is determined by the closest center in Euclidean space. So with these two actions, mean computation labeling, what do? The k-means algorithm starts with randomly initialized centers, J1 through Jk. The labeling step is then executed, and these initial random centers are then used to determine initial labels according to 2.41. The algorithm then iterates over the mean computation step, 240, followed by the labeling step, 241, and repeats the two steps, one after the other. This is done until no more changes are made to the labels and the means. Such an iteration generally does not find an absolute minimum of the objective 239. However, the approximation found is often satisfactory. So we iterate between mean computation labeling. In figure 232, we illustrate the workflow of the algorithm on synthetic data where we choose k equals 3. So we choose exogenously to the data, we just choose k equals 3 clusters. The top left plot is the initialization with 3 random means represented by the black circle, the red triangle, and the green cross. Then each row of figure 212 represents one iteration of the algorithm, where the plots on the left column show the output of mean computation, except for the first row, which was initialization. The plots on the right column show the output of labeling. Let's see it. So first row is the first iteration, second row is the second iteration, third row is third iteration. So we start with initialization here, where we randomly initialize 3 centers. Okay, then we do labeling. We take all of the, for each point, we see which center it's closest to. We see, this point is closest to the center, so it's part of this center. So that is, and we do this for all points, okay? That is called labeling. Now, given these clusters here, which we have for labeling, we can now recompute their centers, okay? So notice in particular that this blue center was previously here, and now it's shifted to the left. Sorry, not the blue, the black circle center. And then we do labeling again. That's on the right-hand side here. And then we compute centers again. And if there's no change between clusters here and here, for example, then we stop. Okay. Then that means the algorithm is converged. Of course, we can also stop in other ways. Note that, and let's also read the footnote. There is a footnote, and I don't see the footnote. It was right here. So this footnote is about initialization, and the footnote says, these may be randomly selected elements of D or some other random sets of vectors. Okay, so there are all kinds of initialization strategies. One way is just to pick 3 random elements. Note that in practice, when presented with data D, one typically first standardizes the data as presented in section 2.1. So subtracting the mean divided by standard deviation. Then the process of selecting the hyperparameter K, which is external to the k-means algorithm, is carried out. One way to do so is to run k-means for increasing values of k and seek a knee point or elbow when plotting 239, that's the loss function, the cost function, as a function of k. As k increases, the objective 239 generally decreases. However, beyond a certain k, the value of adding further clusters further diminishes. In some cases, such as the visual pictorial segmentation we present below, visual subjective measures can be used to find the right K, a suitable K. Okay, so let's see an application. Image segmentation with K-means. We've already briefly discussed image segmentation in section 1.1. See figure 1.2. That's in chapter 1 in that section. As discussed, the goal of image segmentation is to label each pixel of an image with a unique class from a finite number of classes. In chapter 6, we've briefly described a supervised approach called semantic image segmentation, which uses label data, namely class masks, in addition to the image for training. Nevertheless, in the absence of such information, one may still carry out unsupervised image segmentation. One way to carry out this task is to use the k-means clustering algorithm, where each pixel of the image is considered a point in D, and the dimension of each point is typically p equals 3. Red, green, and blue for color images. This can produce impressive image segmentation without any other information except for the image. Figure 2.13 presents the segmentation of the color image, where k-means is used for grouping the pixels into k different clusters. This color image in figure 2.13a is a 640 by 640, which has about 400,000 pixels color image. That's with p equals 3. Here's the image. The segmentation consists of running the k-means algorithm, which groups similar pixels based on their attributes and assigns the attributes of the corresponding cluster center to the pixel in the image. Figure 2.13b presents the result of the segmentation using k equals 6. So if we decide to have 6 clusters. And figure 2.13c does this with k equals 2. That's it. That's the example. Interesting. I actually remember this image. We took it on May 24th, 2015. That was 8 years ago. We had no idea we were working on this book when we took this image. That's in the UQ swimming pool. Anyway, back to business. Matrices and unsupervised learning. We often organize the data D, which is x1 through xn, in the data matrix, xd, similar to the design matrix 210, by stacking each observation vector in a separate row. The difference between the design matrix xd is that the latter does not have the first column of ones. So in 210, we had a design matrix where we had a first column of ones, okay, and then we had the different. Each column was not an observation; each column was a feature. Okay, we still can do this, but we can just do it without the column of ones, and we'll call this XD. Okay, that's as though we don't have an intercept. Thus, XD is an n by p matrix, where the ith column has the data samples for feature I. It is useful to demean the data by defining the center data matrix, and that's similar to the standardization we've done before. So now we take XD and we subtract from it 1 times X bar transpose. So let's see what that is, where we reuse a notation X for the matrix previously used for design matrix. Okay, so now this thing is a centered thing, but it's not a design matrix in the center. It's just reused. All right. And used in the design matrix, and where 1 is a column vector of 1 sublength p. In the centering process, the p-dimensional vector x bar has coordinate x bar I, which are sample mean of the features as defined in 2.1. Okay, so x bar are going to be the sample means of every feature, And this matrix here is an outer product of these, okay, which has the same X bar vector on each row. That is, for each column feature in XD, we subtract the mean of the feature. So this is just a matrix form of representing D meaning, okay, or centering. Thus, the new n by p matrix X has features that each have a sample mean of 0. Okay, so this is a d-meaned X. Okay, this is what this guy is. It's a d-meaned X. An important matrix for such data is the p by p sample covariance matrix. So once you have this X, if you do the gram matrix X transpose X and you divide by n, it's called the sample covariance matrix. Let's look at the footnote. In statistical context, one often uses n minus 1 in the denominator instead of n. For all non-small n, this distinction is insignificant, and we also had a comment like this in section 2.1. Written in scalar form, the ijth element of the symmetric matrix S, which is a covariance matrix, is Sij, which is the sum over all observations K, okay, of the kth observation I minus its mean, and the the kth observations I feature minus the mean, and for the same observation, the jth feature minus the feature mean. So that's the covariance of Sij, of feature I and feature j. And it estimates the covariance between feature I and feature j. On the diagonal of S, where I equals j, SII equals the sample variance S squared, just like we had in equation 2.1 for the sample variance. The off-diagonal entries account for the measure and direction of linear dependence between features. Okay, and of course, S is a symmetric matrix. We note that the sample covariance matrix can be further normalized to a sample correlation matrix by dividing each ij's entry by the product of the sample standard deviations, Si and Sj. Sample correlation matrices are important for multivariate descriptive statistics, yet we do not use them explicitly now. Our focus is rather on PCA, which we introduce in terms of the d-mean data matrix X and the sample covariance matrix S. So in this small section, what we had was X and S, okay? D-mean data and sample covariance matrix. Principal component analysis. It is often the case that not all p dimensions of the data are equally useful. This is especially the case in the presence of high-dimensional data, large p. Moreover, many features may be either completely redundant or uninformative. These cases are referred to as correlated features or noise features, respectively. In such cases and others, principal component analysis, PCA, is often employed. It is a well-known and widely used dimensionality reduction technique applicable to a wide variety of applications such as data compression, feature extraction, and visualization. The basic idea of PCA is to project each point of D, which has many correlated coordinates, onto fewer coordinates called principal components, which are uncorrelated. This is done while still retaining most of the variability present in the data. In this setting, PCA offers a low-dimensional representation of the features that attempt to capture the most important information from the data. PCA does this by creating a new reduced set of features called principal components, indexed by 1 through m, I going 1 through m, where m is less than p, so often much less than p, is some specified lower dimension. For visualization, we often take m to be 2 or m equal 3. In other applications, such as, for example, the integration of PCA as part of other machine learning procedures, m is often calibrated as a hyperparameter. As input, PCA uses the d-mean data from the center data matrix X of 242, what we just did, where we denote by X sub I the ith column of X, corresponding to a vector of feature I for all n observations. PCA uses a linear combination of these columns to arrive at vectors of the new features. Let's call them X tilde 1 through X tilde n. So we have less of the new ones. This can simply be represented as X tilde I is going to be a linear combination of the P columns X1 through XP, where the linear combination weights are VI1, VI2, VIP. Okay. Where each new n-dimensional vector, X tilde I, is a linear combination of the original features. The coefficients of this linear combination can be organized in the vector, so VI, the coefficient for the ith for I, are VI1 to VIP, which is called the loading vector for I. Thus, X tilde I is X, the data matrix X, the d-mean data matrix X, times VI. This can also be represented for all the reduced features and loading vectors together via X tilde 1. So you can look at the vector X tilde 1 is based on the loading vector V1. Right? So it multiplied here. So you had this operation with this vector, etc., etc. So what you have the X tilde n by m, that's a reduced data. That's the original d-mean delta n by p times the matrix of loading vectors v tilde, which is a p by m matrix. It turns out that a very useful way to represent this, to represent loading vectors v1 through vn is by normed eigenvectors associated with eigenvalues of the sample covariance matrix S. Specifically, since S is symmetric and positive semi-definite, the eigenvalues of S are real and non-negative. A fact which allows us to order them via lambda 1 is going to be the greatest one, it's greater than lambda 2, and lambda p is the smallest one. We then pick the loading vector vi to be a normed eigenvector associated with lambda I. So this is if lambda I is an eigenvalue, okay, then vi is a eigenvector associated with that eigenvalue. While keeping in mind that the first loading vector is associated with the highest eigenvalue. Just remember that for every eigenvalue, you have many, many eigenvectors, so all the vectors that satisfy this. So we choose a normed one, the one that has norm 1. L2 norm 1. The second is associated with the second highest eigenvalue, and so forth. The symmetry of S also means that its eigenvectors are orthogonal. That's a property of a symmetric matrix, its eigenvectors are orthogonal. And hence, V tilde, so V tilde that has these guys, is a matrix with orthonormal columns. Okay. In this setting, we assume that at least the first m eigenvalues are strictly positive. So lambda m is a strictly positive eigenvector. In the subsection below, we derive the main result to show why this choice of loading vectors based on eigenvectors is attractive. At this point, let's consider a numerical example. So at this point, up to this point, we simply specified that the way that we choose these loading vectors is just to take them as normalized eigenvectors. Okay, and this will be the way that we project the original d-mean data onto the reduced data. Okay, next section will show why. We return to the Wisconsin breast cancer data used in section 2.2, where P equals 30, so 30 features, and N, the number of observations, 569. To visualize this data using PCA, we set M equals 2 and compute the first two loading vectors from the 30 by 2 matrix V tilde using standard numerical procedures for eigenvalues and eigenvectors. Then by multiplying the 569 by 30 mean data matrix X, so this would be your mean data matrix X. You have 569 by 30. Okay. With by V tilde, so V tilde is going to be 30 by 2, as in 244, we get the 569 by 2 matrix X tilde of principal components. So much thinner matrix. Right? So then, so this new matrix X tilde, let's just write it here, it's going to have PC1 and PC2. Okay, and it has 569 of these. Okay, so each vector like this can now be plotted. We then plot each row, which is a two-dimensional vector in figure 214a. So these are now this is a plot of the principal components. So at this point, this doesn't tell us much. On their own, the two-dimensional points in figure 214a may not be insightful. After all, the principal component coordinates, which we now call PC1 and PC2, do not have any physical meaning in this context. Nevertheless, if we consider figure 214b, where we frame this as a supervised learning model and color the points based on the labels, remember there was benign and malignant, a useful pattern emerges. There's quite a clear separation between the two classes, and hence there's potential to classify points by separating the region in the principal components plane. There's actually a very nice separation between the two. We do not discuss concrete examples of constructing a classifier in this case. We rather point out that the data following a PCA transformation with reduced dimension M less than P can often be used as input to supervised learning algorithm. So we could have continued with here with a supervised learning algorithm. Derivation of PCA. The PCA framework tries to project the data in the direction with maximum variance. Returning to 2.44, let's return a second to 2.44. So this was 2.44. Up here. So you've got your X tilde, your X, and your V tilde. Returning to 2.44, since X tilde I is X times VI, we can formulate this by maximizing the sample variance of components of X tilde I. Keeping in mind that X tilde I is a zero mean vector, so just like X was zero mean, X tilde I is also zero mean vector. Its sample variance using 211 is simply X tilde I transpose times X tilde I divided by N. So no need to demean it. Hence, substituting X tilde I equaling X VI, the sample variance of component I is now going to be, you got this nice thing where you do a transpose and you flip the order, okay? And hence we got this sandwich on the Gram matrix here. And notice that X transpose X over N is just the sample covariance matrix. So the sample variance of component I is VI transpose times S times VI, where S is the sample covariance of the data as in equation 243. Thus, in searching for the first loading vector V1, we have an optimization problem. Basically, we might want to maximize the sample variance of component I. So we might want to maximize this thing, subject to, let's find V to be of norm 1, okay, because that was one constraint we wanted. Note the constraint which seeks a normalized direction V with V1, which is equivalent to V transpose V equals 1. This representation allows us to use a Lagrange multiplier techniques, where we convert this constraint problem to an unconstrained quadratic problem. The objective is then maximization over the V, the vector, and lambda, which is a Lagrange multiplier, okay, of what we wanted to optimize previously. So that's a previous objective here, plus this is the constraint. Or we can write this as, we can just reorder this and write it as this maximization problem. With a Lagrange multiplier lambda and the constraint 1 minus V transpose V equals 0. Now taking derivatives with respect to the vector V, we see also appendix A. So if you take a derivative of this with respect to vector V, we obtain SV minus lambda V. Thus, the first order condition in terms of V reduced to the eigenvalue problem, because if you're now going to equate this to 0, lo and behold, you have your eigenvalue eigenvector equation. This means that any eigenvector V of S adheres to the first order conditions for the optimization problem, 246. By multiplying the eigenvalue equation by V transposed, we get, now we can multiply this guy by V transposed, and you get V transposed SV minus V transposed lambda V equals 0. As apparent from the representation on the right-hand side of 247, this means that any eigenvector yields a maximization objective, which is equal to the corresponding eigenvalue lambda. Hence, the optimization problem is solved by choosing the maximal eigenvalue lambda 1, with V being an associated normalized eigenvector V1 is 245. So we actually see that the maximal eigenvalue lambda 1 is the one to choose. If, and the motivation here was sample variance of component I maximized. The subsequent directions, VI for I being 2 to Q, this Q should be an M, are chosen by maximizing the variance of the new linear combinations, which are orthogonal to previous ones. That is, the directions capture the part of the variance which has not been previously captured. It can be shown that a normalized eigenvector which matches a second eigenvalue, V2, maximizes variance once the direction of V1 is removed. This then continues for I equals 3 up to M, and in summary, principal components are determined via 245, meaning just via the eigenvector, eigenvalue relationship of the covariance matrix. Okay. TCA through SVD. We've already used the singular value decomposition in section 2.3 in the context of the Moore-Penrose pseudo-inverse. We now further revisit the construction of SVD from linear algebra and see the relationship between SVD and PCA. Any n by p dimensional matrix X of rank R can be represented as X is U times delta times V transposed, which can be represented as the sum over I1 to R, R being the rank of the matrix, of delta I times the outer product U VI transposed, with delta being the diagonal of delta R, and delta I being strictly positive. You've got R of those based on the rank. Here, the n by R matrix U and the P by R matrix V are both with orthonormal columns denoted UI and VI respectively, for I going 1 to R. These columns are called the left and right singular vectors respectively. The values delta I in the R by R diagonal matrix delta are called singular values and are ordered from largest to smallest, and they're all strictly positive. Note that this representation of the SVD differs from the one employed near 217. That's when we did the Moore-Pointropes-Sutton inverse in section 2.3, where U and V were taken as square matrices, and delta was not necessarily square. So here delta is square, but U and V are not necessarily square. The form used in section 2.3 is sometimes called the full SVD, and the form we represent here is called the reduced SVD. So we only have singular values based on the rank of the matrix. Consider now X again as a d-mean data matrix 2, 4, 2. So that was just a d-meaned X. Now using its SVD representation in the sample covariance. So sample covariance was just 1 on n X transposed X. But now we just stick in the SVD representation. So for X transposed, when you do a transpose, you flip the order, you get a V delta transpose U transposed. Of course, delta transpose doesn't do anything. Okay, U transpose, and that's X. And then you get this nice thing that this thing that I'm highlighting in blue cancels. U transpose U cancels. Okay, so we obtain that S is 1 on n times V delta squared times V transposed. Okay, because U times U transpose canceled because U is a matrix with orthonormal columns. Okay. And then you've got delta transposed is the singular values squared in the diagonal. Here, the fact that U has orthonormal columns implies that U transpose U is a R by R identity matrix, and hence it cancels out. Hence, S is actually the sum on I going 1 to R on the rank of the data matrix X, okay, of the singular value squared divided by n times these outer products, VI times VI transpose. We can now compare to the eigenvector-based representation of PCA, where V tilde as a matrix of PCA loading vectors is in 2.44. So let's again look at 2.44. 2.44 was this key equation representing PCA, taking the mean data, multiplying it from the right by the matrix of loading vectors, and getting the reduced data. So again, we're saying we can now compare to the eigenvector-based representation of PCA, where V tilde as a matrix of PCA loading vectors is in 2.44. Take M to be R. Okay, so take M to be the full rank of the data matrix, and denote by lambda the diagonal matrix with diagonal entries as eigenvalues of S in decreasing order. So that's it. So let's assume now full rank data. Okay, so that means that gives us this strict lambda R, the smallest eigenvalue, is still strictly positive. Now using 245, we have, so if you go now to 245, which was here, 245 is simply the eigenvalue equation for the matrix S, eigenvalue eigenvector equation for the matrix S. Now, using 245, we have the spectral decomposition of S. You can always do a spectral decomposition of S, which is V tilde transposed times lambda times V tilde, and this is what you call the spectral decomposition of a covariance matrix in this case. So now compare 249 and 250. So now compare these two guys and see that with lambda I being the singular value squared divided by n, the loading vectors in 250 are the right singular vectors in 249. That is, v tilde is v. Further, to obtain the data matrix of principal components, x tilde of 2.44, we set x tilde is xv. Now, using the SVD representation of x, 248 was the SVD representation of x. Here it is. Now, using the SVD representation of x, 248, and assuming n equals r, so full rankedness, PCA can be represented as that is your matrix X times V, which is just U times delta, which is delta 1 times U1, delta 2 times U2, delta R times UR. That is, each column of the reduced data matrix X tilde is a left singular vector UI stretched by the singular value delta. Further, for m less than r, we only take, if m was less than r, we would have taken only the first m columns, and we would have stopped at some point. With these relationships between PCA and SVD, numerical methods for computing the SVD decomposition of x can be used for PCA. Indeed, in practice, efficient and numerically robust computational methods for SVD are employed for PCA. So what we saw in this subsection is that you can position PCA as you can use SVD for PCA, and specifically the reduced data matrix is obtained via those left singular vectors stretched by the singular values. SVD for compression. The singular value decomposition can also be viewed as a means for compressing any matrix X. Specifically, consider the SVD representation in 248. That was just the SVD expression with this decreasing sequence of singular values. Then a rank m less than r approximation of X is, so x tilde is going to be a lower rank approximation of x. So take x to be any data matrix. And instead of summing up to the full R here, you just sum up to m. And you do a sum of these rank one matrices weighted by their singular values, okay? And each one is called, the rank one matrix is obtained via UI times VI transposed. Okay? That's what you do. Where x minus x hat is, this is kind of what remains. The rank of x hat is m, and since one often uses m significantly smaller than r, this is called a low rank approximation. For small enough delta m plus 1, the approximation error is negligible since the summation of rank 1 matrices, delta I, ui, vi transposed, for I, m plus 1 to r is small. Observe that the number of values used in this representation of x is m times 1 plus n plus p, and for small m, this number is generally much smaller than n by p. Okay, so instead of having n, we have here m, and m can be as small as we would like, which is the number of values in x. Hence, this may be viewed as a compression method. The usefulness of such low rank approximation is validated by a theoretical result called the Eckert-Young-Mirsky's theorem. Here we consider the approximation error matrix x minus x hat, and we seek to have the best rank m approximation in terms of minimization of x minus x hat. The theorem works for several types of matrix norms, yet here let us focus on the Frobenius norm. So see, x minus x hat here is a matrix, and we're doing here a matrix norm. Let's look at the footnote, what the Frobenius norm is. This is a square root of the sum of the squared elements of the matrix. So the Frobenius norm is denoted A subscript F for a matrix A. We now have for the Frobenius norm the min x hat of rank M so the closest approximation to X based on the Frobenius norm, okay, Frobenius norm squared, and you can write this difference as follows, okay, so because that is X hat, is the sum of the singular values squared of, so that's what's going to be the minimum. Singular value decomposition-based matrix approximations as 252, so this matrix approximation based on singular value decomposition, are useful in multiple domains, including improvement of neural network model size. We do not discuss these topics specifically in this book. Instead, consider a simple visual example with a 353 by 469 monochrome grayscale image appearing at the bottom right of figure 215. So here we have a figure. That's the original image. Okay. This is X. Then the other images in figure 215 are X hat with M equals 10, M equals 30, and M equals 50. As is evident, the M equals 50 approximation appears close to the original image. So this is this Q should be an M. Okay. So we've got an M equals 10, M equals 30, and M equals 50. Compression. So this is a rank 10 compression, rank 30, rank 50. As evident, M equals 50 approximation appears close to the original image. The main plot in the figure is a relative approximation error as given by the right-hand side of 253. So this would be a relative approximation error, and that's what we're plotting here. Divided by the sum of all singular values squared. Note that the original image uses 353 by 469, so about 165,000 values, while the rank 50 approximation uses, we can compute, only about 40,000 values. That is, the approximation yields X hat, which is compressed to about 25% of the size of X, and looks very similar. Okay. Looks similar. Note that variants of the types of plots in 2.15 are also common when carrying out PCA. In that context, the plot is called a scree plot, and it presents a percentage of variance explained by principal components. So this concludes our section 2.6 of chapter 2. And by this, we also conclude chapter 2. Thank you for bearing with me during this long section. I hope you found it useful. As always, leave comments below to let us know what you think. Thank you.